thank you, organizers, for invitation. It's my great honor to speak to this very distinguished audience. So this is a joint work with Pierre Degan here, and I make from the very blunt close. So it's analysis for dynamics of Doi-Onsager theory on orientational phase transition. So let me just first remind you what Onsager's older question in 1949. He formatted a question to studying orientational phase transition. So he looked at the mean field theorem. Maybe I should point. Yeah, thank you. So look at the distribution. Omega is on Sn minus 1 because it's general dimensional. The mean field distribution. Then you look at sort of quadratic interaction potential for kernel. Then you write down the free energy, the entropy and interactions. Then you so he formulated a question: if you minimize this free energy subject to the probability distribution 1, then you found the states, and this state is going to phase transition. So that's what basically Onsager's picture to understanding the phase transition to in top of the Landau's picture. So that is the question. So this question can also formulate in more formalism in in Doi or Doi-Edwards. So basically, to look at this free energy, you compute the variation of free energy, you can get a chemical potential. So now you have draft velocity v, just minus steep gradient to this chemical potential gradient, and you just transport this distribution as usual theorem. And this is exactly the equation right down Fokker-Planck equation. Or people have different names, like the McKinsey system, Vasek, all kinds of things. Basically, the diffusion and with sort of interaction potential. So that's the equation we have here. And of course, naturally, this formalism tell you naturally organizers have this sort of very easy to see this dissipation of free energy with dissipation given by this quantity. So now this will give you at least a very simple tell you what's the equilibrium states by the Doi formalism. Okay, so let's give you some examples for kernels. And the most important kernel, of course, is Onsager kernel. There are two types of the problem. One is have no direction, one have direction. So studying for polymers is no direction because just rod. So as the Onsager indeed first calculated is free energy by use called exclusive wording. That's how jamming, how the packaging for the interactions. And this is too difficult to study, and let time people have sort of a quadratic term approximation to this original one for a polymer. So there's another type of the interactions for directions, which is for magnets, which is you have the dipolar interactions, and also more motivated for us is studying for birds, flocking for birds. And when flocking birds nearby critical mass, you see the flocking behavior. That's what we're going to emphasize. Let me just give some sort of motivation where we come from. So this is a paper which generated a lot of interest by Vishke in '95, and he sort of tried to simply formulate dynamics for birds, how to do, and just with simple discrete version, time and location and speed, and sort of self-propeller. That means the birds have about its own energy move and unit speed. That's sort of self-propeller means. So you just update. And you pick up the neighborhood alignment. You just birds look along, take a neighborhood average, then you just unit size. You just pick a unit speed, and you put the noise in. That's for dynamic. Indeed, the long calculations have a lot of interesting phenomena, like for this 4 pictures. So the first picture itself basically sort of in a region high temperature or low density. That's equivalent. So basically means that birds are randomly move along. It's no homogeneous. So now the other region itself, with this region itself reverse order, either sort of low temperature or high density. Then you see birds are lined up. You sort of have the flocking behaviors. This first picture what Vishke had. And second picture what he says sort of so invalid. You zoom in, zoom out of the scene. You either like both increase density of temperature or decrease density temperature, and then you see this basically sort of scaling behavior. It's sort of in his numerical calculations. And so this is the Degan and load down this sort of dynamic in continuous version also he's studying the sort of kinetic formulation for the problem. It's a lot of interesting phenomenon because it's non-equilibrium system. All right, so now in the paper itself, another important, basically two parts. And the second part is try to study the sort of phase transition behavior. So these are diagrams in here. So what I have. So what is just fixed density for the problem? You have different birds, but the density is fixed. So they evaluate the temperature or noising. So you as decreasing temperature itself from the very beginning, you see the randomly move along, and the critical points here happens to 3, and you visit the units. Then the bird's going to flock in some direction, and you move on the lineup. So that's the behavior what I have. And then also they try to plot the nearby behavior itself on this part. You just sort of log plot nearby. You zoom for this scaling behavior, sort of basically half. So it's very much like the Landau's signal phase transition picture, like magnets have. So we sort of try to justify this picture. Okay, so just write down the mean field equation, transport equation itself. Of course, the omega is on S2. Then just transport and sort of Fokker-Planck on this side. And for this guy itself, you just look at the equilibrium states. Just take a 0 itself, basically sort of have two types of solution. If density is small, then you just uniform distribution. If density bigger, then you just sort of you have two solutions, either uniform distribution or sort of Maxwellian on sphere or coefficient distribution. The form in this way. I'm going to say more detail how it comes from. Okay, so this basically is omega is a pickup direction, and inner product of omega itself is a K is a sort of carbon concentration. How concentration this direction. I'm going to explain more on this, and this is one. Okay. All right, so let me just only talk about, and it's only last we have also spatial homogeneous. So back to another question. So let me try to remind you what we're going to focus on here. So take this the dipolar interaction kernel and just write down just usual compute this is sort of draft velocity gradient for the car is just basically the projection of the mean velocity or first moments in this tangent direction. So this will give you the dynamic of equation. You have the Fokker-Planck equation on the sphere, and with the projection in this tangent velocity for draft velocity. And of course, we set the formalism of this Doi on the dissipation for free energy. All right. The first question is we need to computer find out all the steady state. Then we should say what's the behavior of this when we try to study the bifurcation, then studying rate of convergence as sort of basic talk. Okay, let me just first just compute all the equilibrium states. So equilibrium states is relatively simple. First of all, because we said chemical potential had to be constant because of the Doi formalism equilibrium state. So basically, write down it just means it had to be in this form. But this form itself, only since kappa itself had to pick up which concentration kappa such that this is indeed a steady state. So that's why by just formalism, distribution 0, chemical potential constant, have this form and this distribution. Now the kappa itself, you just compute the length. Average length for this distribution give all the parameter. I'm going to explain. And this is the kappa k itself, and this gives just simply you just pick up any direction, doesn't matter because then just pick up this function itself and this order parameter. So this order parameter itself is computer. This guy itself can uniquely determine given sigma, the temperature itself. You need to pick up a uniquely concentration parameter kappa, such that make this equal. So this is how to find all the equilibrium states. And this one just simply take a derivative of this guy, come up with this function. And this function with sort of painful calculations on the spherical Homa function, we say indeed this are indeed positive. So that means this guy functions the monotone, strictly monotone decrease from the critical points to 0 and any temperature in between going to only find one solution. So solutions are unique. We found all the solutions. So that's sort of a picture inside here. So for the above this critical temperature itself is of course uniform distribution. Kappa is 0. There's no concentration. And below this one, you have two solutions. One is kappa 0, uniform distribution is unstable. I'm going to explain to you. And another one is with this kappa have a unique concentration coefficient, you found a solution. And the solution itself now is a lot of solutions, because any direction itself will pick up, give you the equilibrium solution. So that's sort of the found other solution. And also for these calculations, you should just indeed satisfy proper Landau's second order fast transition. Mainly, this order parameter is the square root of this critical difference between critical points. Okay. So let me just give you sort of diagram a little bit more. So this is a different way to look at a problem. People like to use called order parameter or average of the average velocity or speed. And if 0, that means if or other way, probably more easy to understand this problem order parameter. Just look at the standard deviation. So indeed, the standard deviation, just flip over this picture, is just exactly means standard deviation. Means define standard deviation exactly calculated 1 minus 6 kappa square root of this. So that's his picture. So normal people doing flow dynamics like studying use the standard deviation instead of use the order parameter, because you want to get 0 means flow. So that's instead of this order parameter go to 1 and standard deviation go to 0, just flip over. That's what we do for flow dynamics. And itself is this concentration, and for people in statistics like to say this more meaningful, the concentration parameter kappa. So that's giving if kappa go to 0, it means it is uniform distribution. I just see how much concentration on these points over here. And now, so we found out all the solutions either if beyond this critical points is a uniform distribution. Below have two states. One is the uniform distribution, another is sort of Fisher distribution. All of that is we also have dimension for any points here. We pick up a unique the kappa and give you the Fisher distribution. And we like to prove this guy is stable, this unstable, as a fast transition. So that's basically the talk I want to say. Okay, so this is a cartoon. It's a cartoon. It's basically sort of called spontaneously symmetric broken. So if the beyond the critical points is the nice have the parabola is the unique minima is the uniform distribution. But below this critical point, the temperature itself, and it's non-convex, and moreover, is have the equilibrium state itself is in a low dimensional Sn minus any point step on Sn minus 1. So and there's energy reverse. So we like to see that is the distribution itself going to the if the going to converging to this one of this equilibrium exponentially. So we'll sort of want to justify this picture. So let me just give you this cartoon really means not it's high dimension, infinite high dimension cannot visual, and also this part is not really now this one is sort of a set of points, but we cannot really plot this nice diagram for MATLAB, so we just make a fake it. Okay, but this is basically picture say how the spontaneously symmetric broken. Okay, all right. So this picture is indeed very easy understanding, either at a linear level completely clear, but sort of rigorously justified rate is takes some more effort. So you just simply take this distribution constant plus perturbation as mean 0, and you just linearize these equations for G, and you just slowly Hamilton and this one, and you mainly to look at this dynamic itself, just look at average velocity or called the G here, or first moment. And this guy itself, you say you have sort of this guy is have a parameter. This magic parameter appears many times, and you see this n minus 1 dimensionality for geometry effects, and this is the 1 over n, the critical temperature subject 1, and this guy either increase or decrease depending on phase transition. Okay, so what we know is if the go to uniform distribution means this is G speed going to average speed going to go 0, and this must be decreased. So this is exactly give you sort of a stable and unstable. It's a linear stable, unstable, but this at the most maximum is 1, so it's sort of a non-linear ceiling turn on. Okay, so let me just now say something a little bit how we approach the problem. So first, sort of cheaper results. Let me just present to you. Indeed, the problem itself, nonlinearity is relatively weak, because this any nonlinearity involved in the first moment, the J involved. This sort of relatively weak nonlinear problem, but still have interesting phase transition behavior. So first get cheap results like this guy. So if the F0 is the initial distribution mean positive, mean 1, and remain positive and mean 1 by maximum principal conservation law. And for any insertive norm s bigger than minus n minus 1 divided by 2, you will see this why this is coming from. I'm going to explain to you why this is a fact. If you beyond this one, then your solutions is a global solution in any superlative norm for the distribution s bigger than this number. So it's around infinity bigger than this. You have a global strong solution. So that was because weak non-linearity for the problem, and also it's give us. And then it's also have sort of spontaneous regularization. Even initially it's very bad, but at the instant time itself, just a heat equation, basically like heat equation, instantaneously will regularize. Let's have instantaneous regularization. Now, so here's sort of the picture. First, give you the Lassé invariant principle. So this is an infinite dimensional problem, but we have regularity, we have compactness. It's basically behave like a finite dimensional. So we found out all the equilibrium states, and this free energy had to decrease, and the compactness is only up to decrease to the equilibrium states. So that's why the guy helps equilibrium state. So now we just that means this guy the distribution go to in the omega limit set is going to converge into equilibrium states. Only question is how to study this rate, how fast they are, and why. So that's we need to do something. So I'm going to give you sort of the cartoon. This is not cartoon. This is really what I'm planning to talk about. So first part is beyond this critical temperature. To prove globally exponential decay, give you a sharp rate on this part. Give you by finding a new entropy. So then this part itself, at least nearby critical point 7, tell you this also exponential decay on this rate. Then of course some part is unstable because if 0, then is like a heat equation. And so that's the picture I like to explain. After this part and this part, I want to explain to you. Okay. So this is basically sort of careful counting or decomposition of field. So you basically use the spherical harmonic function on sphere to Fourier analysis to expand the distribution in the in the space. So just remind you some simple fact about spherical harmonic function. So spherical harmonic function counting basically means homogeneous polynomial of degree L restriction on sphere. That's the definition for spherical harmonic function. And this we denote this degree of L. This M is just dimensional Sn minus 1 dimensional space, and the degree we call the K L minus just the number of the polynomials in this degree of L, counting by this polynomial. Okay, so now this polynomial itself is sort of the Laplace Pochami operator is give you sort of complete argument system by this spherical harmonic that I have. So now we do careful counting sort of need a decomposition like Legendre polynomial or like the ultra spherical polynomial in here. So if for any kind of this spherical harmonic in this space, you can decompose in the way some details. So it will be like the first of all, you have the normal component, pick up any normal component, then cosine theta, sine theta, a projection to the low dimensional. It's a low dimension in Sn minus 2. So it's pick up Sn, any vector in Sn minus 2, you pick up the spherical harmonic function for the m degree for the m. And this K is counting for how many of the spherical function have. Expand this one, it gives us sort of orthogonal polynomial, which is really all the calculations carried out by because realize this orthogonal polynomial behavior called ultra spherical harmonic function. It's kind of a generalized Legendre polynomial. Okay, so here is the way to make it work called a conformal Laplacian operator. Let me just define this guy and learn from the people studying this sharp constant for logarithm, the Harding inequality. Okay, so define this guy. And the one what we motivation, let me try to say why we do this sort of conformal Laplacian. So let's just look at the eigenvalues for Laplace Pochami over here, and this what we know is L plus m minus 2. And we like to fill in gap in between so that we telescope cancel each other. That's sort of looking for cancellation. So that's how we look at this conformal Laplacian. So you for this guy, for n odd or n even, and this sort of basically the high order differential with some sort of some shifting constant. And because this steer graph projection, you need calculations for the one. And this sort of standard people that are studying in the project. So this is the differential operator, and when n even, sort of you take a square root, sort of pseudo differential operator for this one. But the main punchline that this operator only give to mainly property we like to use is sort of this eigenvalues for this guy is by giving this function which we have to do the telescope. Like have. So the telescope was stated by this theorem, this lemma. So for any mean zero distribution, so then it's a Gaussian omega on sphere. This omega is a vector. This is we define this conformal Laplacian Richomy. As h here, this guy can be zero, cancel each other. So that's the cancellation how come from. Okay, that's sort of calculations with sort of special functions. We with many blackboard we writing for the weekends when I make a visit in Duke. All right. So now let me show you. I will not show you this proof this lemma, but I will show you the proof this derive this new entropy. So once I have this cancellation is way this is a fact. Okay. So if write down f equal to 1 plus g again. I choose h is inverse for this Laplace Bernoulli operator, conformal Laplace Bernoulli operator of this guy, and the inner product to this Doi-Onsager equation. Left side get this guy because the 1 is constant, slope is 1, doesn't matter. And this part is pick up this guy, just Laplacian. Now look at nonlinear term. Nonlinear term itself is the f and g are same because this give you a mean velocity here, and 1 plus this one. And the 1 itself. This guy itself, first this Gaussian is in tangential component to take this out, and then this guy is simple geometry calculations itself will give this term itself give you n minus 1 sort of the geometry fact, and this n minus 1 is pick up because only in the first moments. So this is how pick up these coefficients, and then this is go 0 because it's lemma. So that's basically the idea. So now you will see that. So look at this special entropy function itself. You have this relation, and this minus sign positive sign competition between two. So indeed, if in the S1 on circle, early time is in the 204 Peter Constantine and Cavacadis and TT is sort of they also this Fourier analysis. They also have similar terms in the S1 with assuming sort of distribution asymmetric. That's what they have. So now we naturally define this guy. It defines sort of a negative substitutive norm. The norm is defined this way, and this defined this way. Then we have sort of end up sort of entropy. All right. So this is the entropy. What we have here, and the dissipation is computation over here. But this only involves first moment. And this pick up this have the first moments and the high moments. Just take this first moments out, compute this one, you give this magic number. Again, just like what we see in the linearized system. There's this constant. Okay, so this is the n is the one you have. So it basically tell you in this norm is exponential decay with this closing fact. And then of course this of course it has to be negative. So that was why the above the critical temperature you have the exponential decay. And because since this regularity and interpolation in any subgroup norm, you have as long as bigger than this or bigger equal to this constant, then you have this uniformly exponential decay to the equilibrium states when this temperature beyond this critical temperature. And at the critical temperature itself, we know this is a decay. We expect algebraic decay, but we cannot prove it. Okay. So now this first part, like when the sort of beyond the critical temperature is exponentially decay in any subgroup norm by this new entropy. So now we move on to looking at the sort of spontaneous symmetric broken, how we can study this problem. So for any points distribution here, so you're going to run into one for this one, and this is part not completely convex. So we sort of, but we know this strictly decay. So basically, by usually local argument, so you need to be a little more careful. So let me just try to remind you how we do that. Okay, so we just look at this first moments of the Untitled equation. Just take the first moments yourself, and this have nice constant coefficients, and this sort of complications is no way to close it. It's a closure problem, but it doesn't matter because J is independent of the omega I pull out, and this have the smooth is a matrix acting on this one, and this is smooth. So this ODE dynamic itself give you a lot of information to study this one. So this leading term is sort of nonlinear collections for this ODE dynamic itself. So first of all, if initially this distribution is have mean 0, then stay mean 0, basically heat equation. That's everything we like have. So this just converse exponentially with the standard variance for this guy. So now, second, if initially this guy is not 0, by this ODE dynamic, it guarantees for any time this guy is no longer 0. It's always have directions. Symmetric always broken. It's always sort of point some directions. You never be back to the symmetric part. Okay, and this guy itself, so you can come down to this energy where itself. So you come down over here. You may land into this place, and then maybe take infinite time with random. So if you beyond this one, if you're starting from the below this temperature, means 0, free time is 0 here, and this has to decrease. So we're starting we do not know how to prove from this point to here to maybe possible beyond, which we do not know. But as long as you beyond below this temperature itself, now then the limit itself is only on this sort of Sn minus points. So we like to see how the symmetric to pick up direction to get a conversion. Okay, so this is this was said. Okay, so that's basically we're doing the sort of pick up sections which is completely convex. So basically you look at this omega t. So this is not equilibrium states, but intermediate. In middle, where is the point directions you have? Define the mean velocity and have sort of mean directions, and it's sort of directions for J itself. So now, of course, starting this below this critical points, you have floating behavior. So by compactness, is large time enough, and this have to be small. You can expand this coefficients here. You just expanding on this this direction. You first pick up 1. You pick up this Maxwellian or Fisher distribution, and first moments collection, second moments collection is mean 0. It's just doing this form. Just assuming this form. You always just need to pick up this alpha and G. And you want to make it small and remaining small or exponential decay to 0. That's what we like to do. So by the compactness, we know for the T large enough, it has to be small and continuous be small invariant by Lasserre. Okay, so be small. So now we're doing sort of need to get a rate is get the dissipation term. Now, since these are good way to decompose, because in sections which is only in this cross section, you know this direction, so it's completely convex. So you have to do the estimate expand this dissipation in this equilibrium cell locally, and you will see this decay indeed with sort of rate exponentially. And moreover, this ODE dynamic self, you have time regularity. So the converging to the mainly you try to need time regularity. So you have time regularity basically means omega dot time derivative. This guy integration from t to infinity is bounded exponentially. It can decrease. So you have time regularity, then you have the pick up this Lasserre, and you get the convergence, this omega convergence equilibrium. So that's how you get this convergence equilibrium exponentially. And with the rate is linear. It have a actual slope. Let me just try to that's right. Indeed, I try to summarize. So what we say here, so this guy, what we said is by this new entropy, we get global, it's a nice global exponential convergence. And this part, we proved by this Lasserre plus time regularity plus compactness plus sort of cross-section, convexity and cross-section, and you need to show this exponential decay for the rate. So let me just give you, instead of look at the diagram, give more, let me try to summarize what I have said, is that. So the system is, we're studying the phase transition, and this is sort of determined by the order parameter, no, it's the one parameter temperature sigma, and then we know that use the mean velocity as the order parameter to studying the behavior, and there's a threshold critical temperature or critical density depending on what's content you're studying. So this is a unique determinant. So this beyond this threshold itself, that means disordered is a uniform distribution. You have strongly convergence, any sort of norm, exponentially globally independent initial data to the equilibrium states. And below this one, then of course we just said you beginning to not know because Lasserre is just a long time running close enough to equilibrium, then exponential decay, like a diving to the states. And for the sigma equal to critical point itself, we have two entropy. In principle, we have play with two entropy such that I get algebraic decay. We was work quite hard on the problem, we cannot get it so far. So we continue work on this this decay on the algebraically. Okay, so this is sort of maybe also point out some what are we working on. So this first of all just said is algebraic decay rate we are working on, play with two entropy. We still do not have good idea. So maybe people in here can point out some good ideas. So then another, we sort of still do not have sort of zero temperature flocking behavior. So when converging to equilibrium states, we assuming sigma positive, and if sigma go to 0, and I guess many people are studying the questions of zero temperature, how this flocking behavior, because tools what we have here is does not work. That's what we studying. And another, we also proved that because this magnets or the birds are interesting, we also probably a lot of people studying liquid crystal, so we also studying the behavior for this guy, and we base this behavior is a little more complicated because this involves signal moments, and the nearby critical points is a resistance, sandwich has two stable states, and we sort of have the results on beyond or below, but not in middle, not sharp. Not as sharp as we have here. So we are still working on this guy. Then, okay, of course, the usual one, we study mean field limited particles. We're studying sort of modeling for this special inhomogeneity. So that's what we are upon. All right, thank you very much.